Swayam Prabha. Digital India. Educated India.
So, any questions? So, let us look at a very quick application of this theorem. So, where we can apply. So, once again let us consider the XOR function, okay, or the parity function. So, parity function is also known as the XOR function. So, XOR n of x1 up to xn is basically x1 parity up to xn. Okay. So, how can we give a lower bound on this function? Okay. So, let f be the XOR function, and now to give a lower bound I have to choose an epsilon, because if I want to apply this theorem on some function, of course, firstly I choose the function to be whatever it is, and then I have to choose an epsilon. Okay. Only then can I apply this bound. Okay. So, what epsilon do I want to choose? Okay. So, note that the smaller the value of epsilon is, the lesser is the number of free variables, right. So, if epsilon is very small, then I have very small number of free variables that are left. Now, how do you think, I mean how do you proceed? So, let us say I give you some function and I ask you to prove a lower bound using this theorem, or you want to think how would you proceed. So, look at this function parity. So, how many variables do you need for parity to change its value? So, let us say if I restrict parity to some from n to some m many variables, how large should m be so that the value of parity depends, or the value of XOR depends on that many number of variables. So, irrespective of what I restrict the other n minus m variables to be, these m variables should determine the value of XOR. For what value of m is that true? Any guesses? 1, why 1? Exactly. So, irrespective, so look at this function. So, let us say I fix the value of x1 up to x of n minus 1 to be something 0, 1, whatever, something. Now, the value of parity irrespective of that will depend on the value of xn. Okay. So, if xn gets some value, parity will get some value, and for xn to be the other value, parity will be the other value. Right. So, I can fix any one of them. So, that is the idea that I want to use. So, I will choose an epsilon which kind of fixes n minus 1 variables and only one variable remains. Okay. So, I will choose epsilon to be what? One over n. Okay. So, if epsilon is chosen as 1 over n, then m becomes 1. So, only one variable is free. So, then what is this quantity? Expected value of sigma chosen from R n, epsilon n is now 1, L of f sigma. What is this quantity? So, here note that all variables except one variable is fixed, only one variable is free. How large will be the formula size, or at least how large is it? Can you give a lower bound on this? Can it be 0, the formula size? See the, you can, the entire function depends on that one variable now. You have only one variable and the function depends on that. Okay, so the size of the formula cannot be 0. Okay, so it has to depend, I mean that variable has to be present in this formula, right. So this quantity is actually, well, at least 1 over here. Okay. In fact, it is exactly equal to 1. Okay. So we have this, and now we will just apply this theorem over here. So this is greater than or equal to 1, and combining with Subutovskaya's theorem. So by what we have is 1 is at most epsilon to the power 1.5 times L of XOR n plus 1/3. So now just rearranging, what I get is L of XOR n is greater than or equal to, what was my epsilon? Epsilon was 1 by n. So this is greater than or equal to n to the power 1.5, or let me just write it as omega this. Okay. Now, is this the best that we have? Why not? Kravchenko's theorem has already given us a lower bound of n square, right. So this is a weaker lower bound that we are getting, right. But that's okay. I mean, I just wanted to show an application. So Kravchenko's theorem of course gives us a better lower bound. Not only is it a better lower bound, one can actually show that there exist formulas which meet that lower bound, where one can construct a formula of size n square. So that's actually a tight lower bound. Okay. So this is not the best one, but this is just the way in which this theorem can be applied. Okay. So any questions? Yes, there are, you can have such lower bounds for other functions as well. Okay. Other bases, yeah. So the thing, so you see where the crux of this theorem lies in. The crux of this theorem lies in that analysis, that if you have an AND or a OR gate, then if I have a xi leaf on one side of that gate, the other side will not have an xi leaf. That is kind of the crux of this theorem, right, because you use that theorem to show that the size of this, if I look at any fixed variable and if I look at both the values of that variable, it basically the size of the function. So if I fix that variable, the resultant formula reduces by at least 3 for every occurrence of that variable. If that variable occurs Li times, it reduces by a factor of at least 3 times Li. So that is kind of the crux. Now, how can you make such a statement for some other gates? Okay, that is not clear. For AND and OR, it works because the very property of AND and OR gives us that, well, it depends only on one variable for some value. So it is very specific to De Morgan spaces. So everything else is kind of just putting things in place, but that is the essential crux of this entire theorem. Any other questions?
So when will it be 0?
Which one?
The expected value size of formula.
The expected value, when will it be 0? So the expected value will be 0 when that formula takes, I mean when that function has a formula of size 0 for all possible restrictions, right? Huh? Which one should be constant? Exactly, yeah, it has to take, I mean, see, you can have functions which do not depend on any variable, right? You can have a constant function. So what can happen is maybe for some other function, some function, if I restrict it to maybe half the number of bits, the remaining half bits kind of are irrelevant. The function anyway goes to some constant 0 or 1. In that case, the expected size will be 0 for such a restriction, but that those are, I do not know. So, those are very probably restrictive functions, I mean, which in some sense you are saying that it does not depend on half the number of variables or something like that. But parity is one function which depends on each and every bit in some sense. I mean, even if I restrict n minus 1 bits and 1 bit is free, that can decide the value of parity. So, everything boils down to understanding how much do I restrict a function, that how much is taken care of by this epsilon term, okay, and after I restrict by that much, what does the resultant formula look like. Okay. So, here what we know is that if I restrict it by this much quantity, the resultant formula will still have at least one gate, it has to have that one gate. That is why I get this plus greater than equal to 1 bound over here. Okay. So, now I will talk about another function, okay, called the Andreev function. Okay. So, why we want to discuss this function will be clear in a moment. So, we will try to give a, we will discuss this function and we will try to give a lower bound on this function using this theorem, and it can easily be shown that that lower bound and kind of matches the upper bound for that function as well. Okay. And this function will actually again occur, I mean, later on in the course as well. Okay. So, this is a important function. So, what is this function? So, the Andreev function is written as a n. Okay. So, it is a n and it depends on two inputs x and y. Okay. And x comma y are bit strings of length n. Okay. So, you can think of this function as being a map from 0 1 to the power n cross 0 1 to the power n, and it would output a single bit. So, this is not exactly a Boolean function, but we will see what we can do over here. Okay. So, how is this function defined? So, the way this function is defined is as follows. I will give a pictorial view, and that is the best way to understand this is take the variable x or take the string x. So, what we will do is I will divide the string x into n by log n, okay, or I will divide the string x into log n chunks of n by log n bits each. Okay. So, I will have log n many rows and n by log n many columns. Okay. So, this is my variable x. Okay. So, you can think of it this way, that the first n by log n bits is in the first row, the next n by log n bits is in the second row, and so on. and the last n by log n bits is in the last row. Now, what I will do is I will take a XOR of all the bits in a particular row. Okay, so, for each row I will take a XOR of all the bits. Okay, so, XOR of all the n by log n bits. What does that give us? Let us say that gives us some string let us call it as z, and the length of this string is log n, right. Now, what I will do is, so z where size of z is log n. Okay. Now, what I will do is I will use z to index the string y. Okay. So, I have this string y also, okay, and I will use z to index a bit in y, and this is the output of the function. Clear? Because any string of length n can be indexed by a string of length log n. Okay. So, whatever that value is, whatever the value of z is in decimal, I will use it to index it, and that is my value. Okay. So, clear what the function is? So, now what do I want to do? So, any confusion? Z has log n bits, yes. So, let us look at an example. So, suppose z is the string 101. So, what is 101 in decimal? It is 5, right. So, it will look at the 5th position of y. If z is, let us say 111, then it is equal to 7. So, it will look at the 7th position, right. So, basically if z is, let us say a 3-bit string, then it can index a string up to length 8. So, that is the idea, and whatever that value is, whatever the value at that position is, that is the output. So, now any string of length n can be thought of as a function on log n. Assume n is a power of 2 here, it's okay. Can be thought of as a function, can be thought of as a Boolean function, not just a function, as a Boolean function on log n variables. How do you think of a string as a function? How do you think? Huh? Exactly. So, essentially what you are saying is that this is kind of the truth table of that function. So, if I have a function on log n variables, the size of the truth table is 2 to the power log n, which is n. Okay. So, this string is essentially the kind of represents what the output of that function is for each choice of those log n many variables. Okay. So, the string here is the truth table of the function. So, this is kind of like a equivalent way. Okay. So, any function on n variables is essentially a string of length 2 to the power n, and any string of length 2 to the power n is a function on n variables. So, these are two equivalent ways of looking at the same thing, and this only whatever I am saying is for Boolean functions, right, because yeah, for obvious reasons. Okay. So, now what we will do is we will use the following. So, recall this theorem, Riordan-Shannon's theorem. Okay. So, what was Riordan-Shannon's theorem? So, let me just recall it for you. So, Riordan-Shannon's theorem gave us a lower bound on the formula size of any function, okay, over any arbitrary basis. So, it was based on, so Shannon's theorem was for lower bound on the circuit size, and Riordan-Shannon was lower bound on the formula size. Okay. So, essentially what it says is that if I look at any function f, okay, on n variables, then or it kind of said a little more, it said that for most functions on n variable, the formula size is at least 2 to the power n divided by log n. Okay. So, there was a delta also, but we can choose delta to be anything that we want. So, here now I have a function on log n variable. So, what I can say is that by Riordan-Shannon's theorem, there exists a function f on log n variables such that L of f is at least, so 2 to the power log n is n by log of log n is log n. So, we know that there is a function on log n variables for which the complexity, the formula complexity is at least this much. Okay. Now, what I will do is, I have this function. Now, I said that I can think of functions and strings equivalently. Okay. So, look at the corresponding string of length, how much? N, right. So, if I have a function on log n variables, its truth table is of size 2 to the power log n, which is n. Okay. So, let y star be the corresponding string or the string corresponding to f over here. Okay. Of course, this is obvious, but yeah. Now, what I will do is I will just define another function, I think, yeah. So, I will define another function, let. So, I had the function Andreev function a n, which took 2 bits as input. So, now I will define another function a n star, and this is a Boolean function now. This is a function on one string of n variables, which is equal to a n of x on this fixed string y star. Okay. So, what are we trying to do? Okay, what is the intuition? Okay, so, instead of looking at it mechanically, let us try to understand. So, what we are trying to do is using, so we have the Andreev function. Okay. Now, for the Andreev function, I am trying to choose a argument for the second part, okay, which makes it most complex. Okay. So, y star is kind of a string which has very large formula complexity, a formula complexity of this much. So, that is the y star that I choose. So, I fix that as my y star, and now I look at this. Now, what can I say about the formula complexity of a n star, or what can I say about the formula complexity of a n? So, L of a n, and if I look at L of a n star, how do these two compare? So, I want to give, so my goal is to give a lower bound on the formula complexity of a n. Okay. So, that was what my initial goal was. So, I considered a function and I want to consider a lower bound on this formula complexity of this. Now, I have come to another function, I have defined another function a n star. How do these two lower bounds compare? Which should be more? A n, why? Exactly. So, this is a restricted function. So, this is nothing but a restriction of a n, right, and we saw that any restriction has a lower formula, that is for obvious reasons, that here I have 2 n bits, here I have n bits. Okay. So, this is clearly well greater than or equal to this. So, in other words, if I am able to give a lower bound for a n star on the formula size of a n star, I will get a lower bound for a n as well. So, from now on I will only focus on this function. Okay. Okay. So, let me write this. So, lower bound for a n star implies a lower bound for a n. Now, how can I get a lower bound for a n star? So, let us understand the function a n star. Okay. So, anything else? Okay. So, what we will prove is that L of a n star is omega n to the power 2.5 minus small o of 1. Okay. So, we will show that it has a formula complexity of at least n to the power 2.5 minus some small, but we will see what those are. So, yeah, so this will I think take some time. So, I think I will end over here because this will take a little time. So, we will continue this next time. In the meantime, you can actually think how one can design a lower bound for a n star using this Subotovskaya's theorem, but we will come back to this next lecture. Okay, thank you.